Hi students, it is very happy to see you again. Okay, let us discuss another very important topics from the chapter solution. I think you have watched all my previous videos. You are making the notes, you are preparing well. Dear students, you use these times very productively. Otherwise, you will struggle a lot. Okay, let us go to the topics. Colligative properties, that's I am going to take you today. So far we discussed solution, partial pressure, Raoult's law, Henry's law, and we have done some numericals also. This is another topic from the chapter. There is a definition for colligative properties. It is the properties of ideal solution which depends upon number of solutes or moles of solute. Properties which depends upon number of solutes or moles of solutes. Therefore, it's independent of nature of solute. Okay? But students, very careful. Depends upon nature of solvent. That's very, very important. Nature of solvent, only nature of solute, nature of solvent. And I can add some more points. It is a property of ideal solution. Second, it is a property of dilute solution. So, a concentrated solution cannot show colligative properties. Okay. A non-ideal solution also cannot show colligative properties. And this property depends upon nature of solvent, but independent of nature of solute. That is, in terms of solute, it depends upon number only. Only number. Okay? Suppose, for imagination, I will tell you, ant and elephant. Okay? Ant and elephant cannot be solutes, but I will tell you one example. Ant and elephant. I am taking class here, to close this. Suppose ant and elephant both are different in size, large difference in size. Okay? But if they are solute of an ideal solution, colligative property depends upon their number, not the nature. Therefore, 100 ants and 100 elephant in an ideal solution gives same colligative properties. Agree? We have such a molecule. You compare with sodium chloride and a starch. Sodium chloride molecule and starch. Or glucose molecule and starch. Starch is a very big molecule. Glucose is very small molecule as compared to starch. But if they form ideal solution, 100 glucose and 100 starch molecule or 1000 glucose and 1000 starch molecules together gives same colligative properties. Here number is different. 1000 glucose molecule and 100 starch molecule or 500 starch molecule. This is glucose is and starch. This is 1000, this is 500. Its colligative property is greater than this one. Two times. Its colligative property is 2 times in the colligative properties of starch because it has only 100. Okay? Only if they are ideal solutions. That is the meaning. Colligative property depends upon only number of the solute molecules, not the nature. Okay? Yes. Now we can discuss what are the colligative properties. Okay, what are the colligative? There are 4 colligative properties. One is relative lowering of vapor pressure. Relative lowering of vapor pressure, that is delta P divided by P0. Second is elevation in boiling point. Third, depression in freezing point. Depression in freezing point. This is delta TB. This is delta TF. The fourth is osmotic pressure. Osmotic pressure. Pi. These are the colligative properties. Relative lowering of vapor pressure. Okay. Therefore, vapor pressure is not a colligative property. Boiling point is not a colligative property. Only elevation in boiling point is colligative property. Freezing point also not a colligative property. Only depression in freezing point is a colligative property. But osmotic pressure is colligative property. Very careful. You have to learn this title completely. Relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. Okay. We can discuss one by one. The first is relative lowering of vapor pressure. Relative lowering of vapor pressure. Okay. To understand this, I will give you an image. Fine. You have a beautiful solvent. This is solvent. This is solute. What is a solute? Non-volatile. Non-volatile solute. Example, sodium chloride, glucose. Then we can say solid solute. Okay. Now, this phase, this is a solution, an ideal solution of non-volatile solute. In this phase, you have only vapors of solvent. Vapors of solvent. Okay. Solute will not be in the vapor phase because solute is solid or non-volatile. Example is salt solution. You take the salt solution, keep it up bottle. Suppose if it is open bottle, the water will be evaporated, finally you will get the salt there. Because salt will not be vaporized. Imagine in such a case. Yes. Now, suppose you say this is P. A. Solvent is A. Solute B. Solute is B. PA. Vapor pressure of solvent. Okay. Now, we know that vapor pressure of A directly proportional to mole fraction of A in the solution. We have already learned this idea from the Raoult's law. Vapor pressure of A directly proportional to mole fraction of A in the solution. Yes? Or PA is equal to XA into P0A. What is P0A? P0A is the vapor pressure when there is no solute. Okay, that is P0A. Fine. Now, I just change this. PA is equal to 1 minus XB into P0A. Yes? Therefore, PA is equal to P0A minus P0A XB. PA minus P0A is equal to minus P0A XB. Or P0A minus PA is equal, divided by P0A is equal to XB. What is this? P0A is the vapor pressure when A is alone. PA is the vapor pressure of A. Vapor pressure of A. P0 is the vapor pressure of A when A is alone. PA is the vapor pressure of A above the solution. This is greater than this. Therefore, that is delta P divided by P0A. That is called the relative lowering of vapor pressure. Relative lowering of vapor pressure, which is nothing but mole fraction of solute. Mole fraction of solute. What is delta P? Delta P is a decrease in vapor pressure when solute is added. That is called the lowering of vapor pressure. Delta P is the lowering of vapor pressure. When solute P is added, vapor pressure is decreased. That is delta P. Delta P is called the lowering of vapor pressure divided by P0A. What is P0A? Vapor pressure of pure solvent. Therefore, delta P divided by P0A is called the relative lowering of vapor pressure. That is equal to mole fraction of solute. The meaning, how much vapor pressure has been decreased, that has been equal to mole fraction of solute. If you have more solute here, here will be less pressure. Agree? Very good. Why? Why that? You know, I said solute is not vaporized. The vaporization happens from surface phenomena. Therefore, you know, if there is no solute, it would have been solvent. If there is no solute here, it would have been solvent. Everything will vaporize. Everything will vaporize. But if there is a solute, some solute will occupy some position like this. This solute will not move away from here. Therefore, it permanently block those routes for the vaporization. Now only this much can be vaporized. Okay. Therefore, when number of solute increases, vaporization decreases, vapor pressure will decrease. Okay. Therefore, delta P divided by P0A is directly proportional to, or delta P directly proportional to. We can say that delta P, lowering of vapor pressure, directly proportional to XB, mole fraction of solute. How much vapor pressure decrease? The magnitude of decrease of vapor pressure directly proportional to mole fraction of solute. That can be mathematically derived from this equation. Okay, fine. Now, there will be numericals based on this equation. There will be numericals. We can have some numericals. Delta P delta P divided by P0 A is equal to XP, that is NP divided by NA plus NP. Now, what is NP? NP is equal to WB divided by MP. NA is equal to WA divided by MA. MA is the molar mass of a solvent. NB is the molar mass of solute. Now, we have already stated that colligative properties are shown by ideal solution or very dilute solution. Very dilute solution means there is very less amount of solute. Therefore, normally the value of NB is very small. NB is here and here. When you compare this value, NP, number of moles of solute, with the number of moles of solvent, this is very small. This is very small. Fine. Therefore, you can neglect this. You can neglect this. That neglection is done for the convenience of solving the numericals. Only for solving numericals. And I am not recommending you that you always neglect that. That depends upon you. You can neglect only if that value is very small. That you will get the idea when you do the numericals. Anyway, finally you will get delta P divided by P0A is equal to WB divided by NP. What is NA? WA all divided by MA. Therefore, MA will in the numerator. Now, this is the equation you can use for solving numericals. Now, many students have the confusion of solving the numericals, where I use the Raoult's law, where I use the relative lowering of vapor pressure. Because the Raoult's law also contains the term vapor pressure, pure pressure, etc. etc. Therefore, I will tell you P total is equal to PA plus PB, or P total is equal to P0A plus P0A minus P0B divided by XB, like that. This equation, or PA is equal to P0A into XA, PB is equal to P0B into XB. These equations are used when you have a liquid solution. That is, solvent is liquid, solute is liquid. This equation, delta P divided by P0A is equal to WB divided by NP, MA divided by WA. This equation is used liquid solid solution. The solid solution. That is, you have a non-volatile solute. Therefore, you be careful about in the situations where these equations are used. Otherwise, you will be confused. Okay, I will give you two numericals from NCERT where both equations are used. Okay, you can go that numericals. Okay, the first numerical, please write down. An aqueous solution. An aqueous solution of 2% non-volatile solute exerts a pressure of 1.004 bar at the normal boiling point of the solvent. What is the molecular mass of? Solute? Okay? Yes. An aqueous solution of 2% non-volatile solute exerts a pressure of 1.004 bar at the normal boiling point of the solvent. What is the molecular mass of solute? Yes. Non-volatile solute. That keyword, that's a keyword that will give you an idea that this numerical should be solved using relative lowering of vapor pressure. Okay. Then we want to calculate molecular mass of solute, that is Mp. Therefore, our delta P divided by P0A is equal to WB MA divided by WA into MP into WA. This is our equation. Okay. Now we want to calculate this. Yes. An aqueous solution of 2% non-volatile solute exert at pressure. Aqueous solution exert this pressure. Therefore, what is this? Aqueous solution of 2% non-volatile solute. Therefore, this is nothing but a PA, that is 1.004. At the normal boiling point, therefore, at the normal boiling point, what is a P0? Here the water is mentioned. So aqueous solution means solvent is water. What is the pure vapor pressure of water at the normal boiling point? What is P0? What is the pure vapor pressure of water at the boiling point? That is 1.013. You have to by heart it. Okay? Yes. Therefore, you will get the delta P. Delta P is equal to 1.013 minus 1.004. Okay? 9. Yes. 0.009. Okay. Now, you got the P0M. Now we want to calculate this. We want to know WB. What is W? Mass of solute. That is nothing but 2 gram, because 2%. What is MA? Molar mass of water. That is 18 gram. What is WA? Mass of solvent. An aqueous solution 2% non-volatile solute. Therefore, 2% is taken as 2 gram. Therefore, this is 98 gram. Therefore, the final calculation, that is 9 into 10 raised to minus 3, I write like this, divided by 1.013 is equal to, what is WB? 2, MA 80 divided by MP into 98. Okay? Therefore, the final answer would be 41.35 gram mole raised to minus 1. This is the final answer. Okay, you solve it. You take this here, and get the MP. Now let us go to the next question. Next question. Heptane and octane form ideal solution at 373 Kelvin. The vapor pressure of the two liquid components are 2 kilopascal and 46.8 kilopascal. respectively. What will be the vapor pressure of a mixture of 26 gram of heptane and 35 gram of octane. Heptane and octane form an ideal solution. Okay. The vapor pressure of the two liquid components are therefore P0 heptane, P0 octane, 105.2 kilopascal, 46.8 kilopascal. What will be the vapor pressure of the mixture? They are asking you a total vapor pressure when W heptane 26 gram, W octane 35 gram. P total is equal to P heptane plus P octane. What is P heptane? P heptane is equal to mole fraction of heptane into P0 heptane. Okay. P octane is equal to mole fraction of octane into P0 octane. Now you know this, but you have to calculate the mole fractions. How do you calculate the mole fraction? Mole fraction of heptane is equal to number of moles of heptane divided by number of moles of octane plus number of moles of heptane. First we can calculate number of moles of heptane. Number of moles of heptane is 26 gram. Mass of the heptane divided by molar mass 100. Number of moles of octane is equal to 35 divided by 114. This is 0.26. This is 0.31. Therefore, this is 0.26 divided by 0.26 plus 0.31. What is that value? That is 0.456. Number of moles of heptane is known. Now, number of moles of octane. Number of moles of octane is equal to 1 minus number of moles of heptane. That is 0.544. Therefore, you got this. Okay. Now we can calculate P heptane. That is 0.456 into 105.2. What is that value? That is 47.97. P octane is equal to 0.544 plus into 46.8. That is 25.46. Therefore, P total vapor pressure of that solution. Their solution is equal to this plus this. That is 73.43 kilopascal. Okay. Yes. I hope these numericals are okay. You solve more numericals and you will get the more idea. Thank you.